All right. Thank you, guys, for inviting me and for a nice introduction. It's good to be here to hear all these nice talks and enjoy beautiful weather in Luxembourg. So today I wanted to talk about some of the more recent results, but all grouped into this umbrella of, some people call it plug and play methods. So those are the methods, class of methods that we use to solve inverse problems in imaging by combining neural networks that are based pre-trained as additive wide Gaussian denoisers with specific sensor models of an imaging systems we want to use. Okay, and the key point here is there's a mismatch between the neural network, which is a denoiser, has no information about the physical forward model, and the actual task you're trying to solve, which could be in microscopy, MRI, something else, right? So you pretend there's no distinction, you still use it and you apply. Now, the reason this is a powerful approach is because denoisers have turned out to be extremely powerful ways to represent images. Now, before I'm gonna jump into this technical aspect, I just want to say that everything I'm gonna present was team effort. What people you see on the screen are very talented students working in my team, and everything you see have had contributions there. It's not my individual work. So I should give credits to those who are in the photo, and then some who actually contributed who are also not in the photo or underneath. So thanks to my team for that. Now, let me kick off by starting by saying motivating the use of denoisers. Okay, so anybody who has looked or heard or seen the concept of diffusion models or generative models, it might surprise you, but the underlying technology underlying diffusion models is a representation of images or videos or visual information by using image denoisers. Now that sounds surprising, but the whole art of it is that images are high dimensional structures that we cannot easily capture with mathematical model I can put on a board. So I need a way to represent it. And usually we use convolutional neural networks or neural networks, and images turned out to be. So this is a nice demo that I pulled out. And whatever you see here is all generated by a diffusion, and of course curated by an artist whose link is provided on the bottom of the site to create this very nice trailer. The full trailer is actually amazing because there's also voice in there. So there is a voice part of this demo, which is also nicely done. All right. But today I'm going to focus not on purely generative. I'm going to talk about generative models as well, but I'm going to really focus on imaging inverse problems. Okay. So we've heard about imaging inverse problems. Those are the type of problems where I have measurements Y, but I don't want Y. I want to get X. Okay. And I want to get access to X. Unfortunately, I cannot measure the X. So all I can measure is use the instrument, the sensor model to get Y. Usually I do know something about my sensor. So A is my sensing model, and A matrix, or it could be nonlinear operator as well, represent all the physics of the data acquisition. Now there's also this little E here, that's noise, because my sensor models or measurements are inaccurate. So we use the models that has some form of noise that we add to this one as well. Now the task is, of course, to get images back from the measurements. Now, this model, which is very simple inverse problem model, has been studied for many, many, many years, starting from the 20th century. But it's a big source of inspiration for my research because it allows me in one concise way to address many problems, going from, bioimaging, medical imaging, and also image restoration task. All these problems can be set up in the same mathematical language, which now allows me to apply the same algorithms developed to different applications, which is something I really enjoy doing. All right, so let me give you two examples. Most of you are familiar with those examples, but if you're not, I think this slides will be useful. So the very first example is a classical magnetic resonance imaging system. So MRI is an imaging system where, unlike my pocket camera here, I cannot take a snapshot of photo right away. So instead of doing this, we use this device to collect frequency information or Fourier information. So it's an indirect way of imaging. So we're going to collect everything in what people call K-space, which is basically the spatial frequency space. By filling in the frequencies through the machine, I can take inverse Fourier transform and form an image like that, right? And then there's a direct link. Now, the problem is MRI is sequential acquisition system. So it is slow, and which between amount of time you spend on collecting data and the quality of images you obtain. So basically means longer data collection would lead to better images, but also means there's discomfort in laying in that machine and waiting for the scan to be over, right? So that's one example. And of course, here's the something like this. This is a radial MRI scan for people familiar. If you try to cut it to 2 minutes or 1 minute, which is something that would be amazing, images suffer from artifacts because of the lack of frequency data that we didn't collect. So the streaking artifacts that you see. Okay. Now the second application is maybe more familiar to some, but overall also less familiar. So let me explain. It's intensity diffraction tomography. So it's a microscopy setup, and I'm going to show you some results with IDT later. It's a very cheap or a simple microscopy setup where we have LED array. That's our light source. You put a sample, there's objective lens, and everything goes through and finally is collected on a digital camera. So a relatively straightforward thing. How does it work? Well, you're going to illuminate one of the LEDs. The light from the LED goes through the sample, gets scattered by the sample. So the light interacts with the object, right? It goes through the thing. And finally, we take an image, which is an intensity image. Okay, so you collect one intensity image for that LED. And just like in tomography, what you're going to do, you're going to illuminate another LED. Right, so you're going to illuminate, it's going to go through, you're going to get another image, right? So the reason it's tomographic is because I can illuminate each LED separately, and I'm going to get access to a certain angle of measurements around the sample. And the goal is once I have those usually hundreds or thousands of 2D measurements, my goal is to form a 3D image of the object, just like in tomography. But the image we're after is a refractive index distribution or refractive index map of the object. For every location in this volume, there's a complex number, and that complex valued number is a refractive index. So the real part is absorption. The imaginary part is scattering of light. So if you have it now, I can plot it, and I see something like this for this. All right. And then IDT is very data-intensive application. As you can imagine, those images could be gigapixel images. We have hundreds or thousands of them, and we finally want to do 3D imaging. And it's also nonlinear imaging inverse problems because there's a phase loss because we can count, we get only intensity measurements. And the second thing, there's light scattering, which might be nonlinear interaction between the refractive index and the light. Okay, so people can linearize it, but in principle, it's a nonlinear relationship. All right, so there are classical issues that we would like to address, and that will be the motivation for my talk. So the classical issues in imaging and problems, first is that acquisition is usually too slow or costly, right? I gave you an example. Usually it's because of sequential and indirect acquisition, right? In IDT, you get intensity images, MRI, you get frequencies, and it's sequential. You trade off the time to quality, right? That's what the reason it might be too cost. And the costly might be the cost of the sensing and so on and so forth. The second challenge we're going to look into is reconstructed images contain artifacts. So here I gave you 3 samples. So one is MRI. You can see those streaking artifacts because of subsampling. This is an IDT image, so 3D IDT image. We're going through the slices. What you see is that there's a fusion between the slices. So the low axial resolution because we have a missing cone there. So not all the data is collected. So you can see there's the axial sectioning is not so good. And finally, this is something probably you don't recognize at all because this is a limited angle CT of a suitcase. Typically security applications, what you want to do is see inside, but the angles are too limited. You just don't get any information, and this is missing angle artifacts, right? That's something we want to address across. And finally, high computational memory requirements, because usually we are going toward 3D images, so 3 spatial, 4D, XYZ and time, space-time, 5D, XYZ time, spectrum, and so on, right? So that's we keep on adding new and new dimensions to the image. All right, so today I basically picked 3 topics that I found to be quite interesting in the recent results that we've done. The first will be a new variant of plug and play that I'm going to talk about in the context of blind inverse problems. So blind inverse problems are inverse problems where we don't have the measurement operator exactly. And that's something we're going to get into. Then I'm going to talk about using implicit representation of images. There was a speaker actually yesterday who talked about implicit representation of images, but we're going to combine it with regularization in plug and play and try to recover neural network represented images which are off the grid, right? They're not on a discrete grid of images. And finally, we're going to talk about diffusion models, also generative models, and try to address extreme missing angle artifacts by using generative models to see what we can get with those. All right. So let's talk with plug and play. We got a nice introduction to plug and play from Eve. I also wanted to say, if you are interested in plug and plays, there's a tutorial paper that came out in January in a signal processing magazine. It's has a code associated with it. There's a paper with it and a preprint. You can access it, and it tries to cover the history, evolution, and some of the theory of plug and play up to January of this year. So could be a good resource. If you don't get the link, you can come by and I can tell you how to get it. All right, so let me start off this by saying it's very common to use probabilistic reasoning to trying to solve inverse problems. They're ill-posed, right? I already explained to you. We have missing data, there's noise. So how can we address it? So very common approach to say, look, the way we're going to address it is by creating a probabilistic model. So what do we say? Well, I know my measurement model, that's YX plus E. I don't know X. I might not know E. So what I'm going to do, introduce probability distribution for both, right? So E, we can say, oh, it's a measurement noise, could be Gaussian or Poisson noise model. You pick your favorite probability and you're going to say noise model. But now the tricky part comes the image prior, right? How do we represent images? They're high dimensional, they're highly structured. There have been a lot of activity there for the past, 80 years and beyond about trying to represent images. But if you could represent images somehow, let's say we do have access to PX, now we could do interesting things. Like, for example, I could design, before I go to designing estimators. So the PX, we know certain things. We know it's high dimensional, right? Because images are high dimensional. We also know it's nonlinear. What do I mean by nonlinear? If I add two images, for example, those two images, I'm not going to necessarily get a meaningful image. But also there's somehow lower dimensional subsets of a high dimensional space. Why do we know it? Well, because you can compress images, right? You can take JPEG compression and so on. We know they're compressible, right? So essentially, we're trying to identify some kind of representation that is lower dimensional than the ambient pixel representation. And that's kind of the goal. But if you do manage to get this form of PX that can generate from that space, or not space, but subset, then you could try to do interesting things, like, for example, design a statistical estimator. So here, what I put here is a maximum posterior probability estimator or map estimator, where you put your measurement model and the Gaussian noise assumption, and now you're going to put negative log of your prior, because we assume you know it. You set it up, and you run your optimization algorithm to minimize it if you could it, and now you're going to get the most probable image according to your model, right? That's a mini. Now, a very interesting sub-example of an inverse problem is image denoising. And this is going to be kind of a focus today of using the image denoising. So image denoising is exactly the same, except you set A to be identity, okay? In image denoising case, we assume no knowledge of the physics. All I'm saying is I have noise, it's additive white Gaussian noise. I want to remove it, okay? My whole premise of my talk is the fact that this type of operator, the noises, takes noises, noisy image as an input, gives clean image as an output, is a great way to represent high dimensional probabilities. It's a great proxy. So instead of directly representing PX or learning PX, we're going to try to get a denoiser. Now, by having a denoiser, now we're going to try to build estimators. And this is the idea behind plug and play, but also diffusion models that are generative models that are used currently. Both are built on the similar premise. All right, so let's go now to try to design the actual algorithm. So Eve explained this, but I'm going to just give you 3 steps. The very first step is we're going to design a learn denoiser. So what do I mean? You're going to take your type of images. So they could be microscopy images, they could be MRI images. You collect them. You're going to add additive white Gaussian noise to them. So just purely synthetic noise to them. And you're going to train a neural network to remove that noise. So you're ignoring all the physics, huh? So it shouldn't shock you. We're ignoring everything to be physics. We're just adding additive white Gaussian noise, and we're removing additive white Gaussian noise. But here's the deal. Even though I just have a denoiser, I can use it. How? I'm going to combine it with something else. Well, we can eventually combine it, but in practice, usually, we're going to train a denoiser to be for different levels of noise. Okay, so we're not going to train one denoiser. We're going to have some sigma control, where sigma is 0, means you have identity, you're not denoising. Sigma is larger value, means you're imposing more and more information from the CNN to try to remove the noise. So we want to have that control. So in practice, we do that. Now, once you have it, the second thing we're going to do is we're going to combine it with a physical model. So the first one packages a prior. The second one packages just the measurement model, the physics model. How do we do it? So there are several ways to do, but very easy one is to say, oh, you know what? I have my data term, which is simply y minus ax squared. So this is for Gaussian noise. That's where my physics is embedded, right? I'm going to take a gradient of it, and I'm going to do a negative gradient step. So I'm going to do a gradient descent step with respect to my data term. One step, and that step going to go from less measurement consistent to a more measurement consistent, while the denoiser goes from more noisy to less noisy. So now you have two of those. One tries to push you towards data consistency operator. The second operator tries to remove noise. Okay, one knows the physics. The second doesn't know the physics. It's only trying to represent the image space. Okay, so image set. Right now, what we're going to do, we're going to just put it together. So here's one way to putting it together. It's called a plug and play PGM or a plug and splitting. You're going to first do a gradient descent step with respect to the physical model, and simply going to pass that intermediate image through a denoiser. Okay, you're going to ignore the fact it might not be just a noise or something. You're going to just iterate between these two things. Okay, and surprise, surprise, if you do this, this works extremely well. There's some theoretical justification for it. I might explain some of it, but this in practice works. But another way to think, you can think of this as the actual neural network, because if I put it into certain t iterations, I have a neural network which has physical component to it, which is fixed, and also the learned component to it, which is a CNN, and I just run it for t steps. I get the output, and that's my solution. Right? So far, so good. So those type of methods, they're known as plug and play methods. Why? Because I can easily plug out one physical model, plug in another physical model. I can plug out neural network, plug in another neural network. Essentially, if a more better convolutional neural network appears tomorrow, I can just plug it into the same algorithm and leverage it in a better way. If tomorrow I realize my sensor model is less accurate and I want to do a more sophisticated one, I just remove that and put it in there. So I can easily update those algorithms as new technology comes through. And that's what their key drivers are very flexible. Another motivation for using, they have very elegant mathematical interpretation behind it. There's been a lot of work on it. I'm going to cover some of it, but it's very satisfying to work with something that has kind of elegant math handling. And finally, the performance is also extraordinarily good if you use state-of-the-art neural networks and good physical models. All right, so let me give you one example. There are many examples if you go to the tutorial paper of how plug and play is used. So this is just to show you how much better you can do with plug and play compared to, very well-known methods in MRI. So this is a 3D MRI. This is a brain. On the left, you have a grappa. If you're familiar with it, this used to be state-of-the-art reconstruction in MRI. It's based on learning, but a very rudimentary learning. It's linear learning of a linear interpolator in the frequency space. And plug and play, of course, has a CNN denoiser combined with the MRI model. You iterate it, you run it. And then this is 10 times acceleration. You can see the classical methods, you start failing at that, right? So the acquisition here is 1 minute, 12 seconds to get this brain image. And then plug and play gets you a really good image. In fact, if you didn't recognize this as my brain, I was part of this acquisition. If I would put all the slices together and it gets surfaced, maybe you could recognize me. But plug and play was tested even in my brain. I think I didn't see anything missing in the details. All right, so now let me give you like a very basic theory. So when plug and play methods came about, people asked, okay, you're just going wild there, you're plugging in a CNN into this thing, is it stable? What can we say about it? In the beginning, we couldn't say too much about it, but over time, people have filled in lots of gaps and we're getting a better understanding. There's still a lot of active research on this topic. So very basic understanding of it can come from monotone operator theory. If anybody familiar with it, there's a nice book by Bauschke and Combat about it with very formal derivations of it. But if you basically apply it to this type of operators, you can get some theorem of the following flavor. If you like this kind of things, I really enjoy this. So I can just say, so if you run this algorithm in the format that I explained you, right? And you're going to assume that your data fidelity term, this is your data term, is smooth, meaning it's differentiable and has continuous gradient with Lipschitz constant L. Then you're going to assume your denoiser is non-expansive, meaning it is Lipschitz 1, and you do this averaging with it. It's called average, or formally non-expansive is a special case of averaging. And finally, you pick a small enough step size, then you can show that basically plug and play priors method will converge. Okay. Now, that might be very unsatisfactory to you because it doesn't tell you what it converges to. You need a little more, because unlike optimization method, you're not doing optimization. You have a CNN that doesn't necessarily link to optimization thing, and you have a data fidelity, but at least know it can be stable. But the problem here, the problem here was that you need to train your denoiser to be non-expansive, which could be a tricky business to try to do if you haven't done it. But we're going to see we can go beyond the theory in a second. All right. So now let me just explain you. So what I explained to you now was you can train a denoiser on images. So whatever problem you have, take images, add additive white Gaussian noise, train a denoiser, and just apply it, right? Now, can you go beyond? What if your inverse problem is blind, meaning you don't know the forward model neither? In fact, turns out the same strategy can be applied beyond images. You can train denoiser for other quantities in your inverse problem as well, and now set up a joint estimation problem, and that's something I want to talk to you now. So the blind inverse problem setting I'm going to consider is the same one that I said, but except now the forward operator, the measurement operator A, has unknown parameters. Okay, I don't know it exactly. In different applications, a different set of known parameters, like tachography, it could be the probe. I will give you some more images. But what we're going to do is we're going to take the same probabilistic model. Now I'm going to say, okay, I have an image prior on this V. I changed X to V because it's going to be more convenient for my notation later. And then phi will be the parameters of the sensor model. Okay, so two classical examples of blind problems. One is could be blind deblurring. So where I say, oh, I have an image, I have some kind of blur kernel, usually motion blur kernel or some kind of microscopy blur. I convolve them and I get a blurry image, right? But I don't know I don't know image and I don't know the blur. So I want to try to split one thing into two, which is normally an impossible task. But don't forget, we have kind of a models to introduce to try to separate them as much as we can. And the second example is parallel MRI. In parallel MRI, we have different coils that collect the data. We don't have one coil, usually 32 or nowadays 64 coils. Each coil has a sensitivity map. That's where the coil is sensitive, collects the data. So if I have an image and say 16 sensitivity maps, by multiplying image for each one, I'm going to get what each coil would see. Then I take a Fourier transform of that to go to the K-space. And if I would subsample it, I would get the actual measurement data. So the model looks like this. There's pointwise for each coil I, there's pointwise multiplication between image and coil sensitivity, Fourier transform, subsampling, and that gives you the coil image, and you do it 32 times. And now the goal is, given that, go back to the image at V, and then also potentially phi depends on the anatomy of the person you're scanning, because they will not be always placed the same way. So you'll need to estimate on each sample. All right. Now I want to just show you the extension of plug and play, which is called the block coordinate plug and play algorithm. So the way we're going to look at it is we're going to say, oh, you know, it's just like the same type of algorithm, except instead of one unknown quantity, I have B unknown quantities. Image is one. Then each coil sensitivity could be another parameter. So like there are a group of unknown quantities, and I want to estimate them all together as this X. Okay, so X1 through XP. I'm going to call them blocks. Okay, so those are your blocks of data, and you're trying to estimate those. Okay, so each block. So in the case of the blurring, one block would be the image, and the second block would be the blur. Okay, the way we do it, well, we're going to introduce the block operator, so I can compute the gradient with respect to each block. So gradient with respect to first block, gradient with respect to B block. If I would put them all together, I would get the full gradient with respect to the data fidelity term, right? And then what we're going to do, we're going to train separate denoisers for each block. Okay, it's the same way. A CNN, put it in, train the noise. So I'm going to have a separate denoiser on each unknown quantity, and I have the data fidelity term. Right now, if I have this two, I can just put it together in a very simple extension of the previous algorithm, where instead of just doing one block, I'm going to have B blocks. And at each iteration, I'm going to just update one block at a time. Okay, so I'm going to update next iteration. I'm going to update the blur. Then I'm going to update the image. Then I'm going to update the blur. How do I update it? Well, I do the gradient with respect to that block. Then I'm going to denoise that block. and I'm going to just iterate that thing. Now, the question is, how do we select the block? So at each iteration, I'm selecting the block IK in this representation here. How do I select it? Well, you can do randomized selection, depending how many blocks, or you can do sequential, meaning you predefine 1 through B, you just sequentially go through them. That's a choice to you. Both can be theoretically analyzed and proven to work in this case. Yeah, that's algorithm. Now, what's interesting is that if you do the thing, the plug and play works remarkably well, even when your prior is not on an image. Okay, so it's maybe hard to see here, but this is an illustration of a coil sensitivity estimation and reconstruction in MRI. So what you see here is a ground truth image and ground truth coil sensitivity map. You can see the sensor is somewhere here because you have a strongest response here. This is the image. And in here, what I show you is iterations of this algorithm. As you run this algorithm, the accuracy of both get better and better and better by using the denoisers on both of them iterations. I'll give you, by the way, there are many more results on the paper, and I'm going to show you some more. So if you kind of put this all together, one thing you can notice, so this is the block coordinate plug and play. We plot root mean square error and structured similarity index metric. So if you put this, if you take Oracle plug and plays that knows exactly the calibration parameters, meaning coil sensitivity maps, you can approach pretty close to it by being able to define priors over both sets of unknowns. So it's a pretty powerful network. And again, the power comes from the fact that ability of denoisers to represent different types of data and being able to integrate them through a data fidelity term. And this is a blind blurring example. So the bad guy here is the first plug and play is the one which you pre-estimate the blur with some method and you fix it. You run your algorithm, you're going to see that the quality of that, so that it's root mean square kind of starts going up. It doesn't get a good solution. But if you keep on updating also the blur kernel, you're going to do significantly better. This is a ground truth kernel. This is the estimated blur. This is a fixed blur pre-estimated and put inside plug and play. This is just a simple illustration, but of course you can compare with different types of methods and again see that it really can be powerful in terms of solving blind inverse problems. And finally, like one thing you can notice here, I didn't say anything about convergent theory. And one interesting thing is in all these applications, what I showed you, we didn't train the image denoiser to be non-expansive. It was just a convolutional neural network trained to minimize the MSE we didn't care anything about convergent theory, non-expansiveness, and so on. But if you look at it, it's relatively stable for both sequential and random selection of blocks. So you can just randomly alternate or sequentially predefine. You can see this is a convergence in terms of image, convergence in terms of parameter. It's pretty stable in both. And in fact, this is something you can perfectly analyze and give theoretical foundations to. It's also part of that paper. But justification comes from the fact that we're training our denoisers, each denoiser for each block, to be an approximation of mean square error, right? How do we do it? We're minimizing L2 loss, okay? So each denoiser is trained to be an L2 minimizing denoiser. Of course, there's approximation here because we don't get access to the true MMSE estimator. We're trying to get it through empirical approximation using real data, right? So we don't get the true denoiser, which is MMSE, but there is an approximation error here. But once we have it and we run, then you can actually analyze this kind of algorithm. And this is a little theorem. Of course, you can find the details in the paper. So if you would run the algorithm I just presented by using sequential updates, random, you can get similar theory, independent blocks, differentiable data fidelity term, approximate MMSE denoiser with some error term epsilon k. So at each error iteration, your approximation error is epsilon because you not have the true. And then if you run it, there will exist some function HMMSE. If you look at paper, we give the expression. It's not a pretty one, but it will exist such that this algorithm will converge to a stationary point of that function, right? So, well, converge meaning that if you would look at the sum of TB gradients, this quantity will be bounded by two things. The first one goes down by T, right? You can see 1 over T here. This is fixed, this is fixed. And the second one has a mean squared sum of all the error terms. What does this mean? If those error terms are square summable, you're going to get exactly the stationary point of that loss. If they're not square summable, you're going to get up to whatever error you're making with respect to the MMSE term. So there is an error, but it will be perfectly characterized by this, the gap you're making in this approximation here. Okay, so if you have infinitely many data in your Shurikat MMS estimator, there'll be no error. In practice, there'll be some error. But if you backtrack and you look at this, this is essentially the behavior you're seeing. You're going to converge nicely up to that error term, after which you will not. All right. So far, so good about the plug and play. I'm going to leave space for the questions at the end. So let me just continue to present you some other ideas. So let me summarize what I talked about. So what was plug and play? Plug and play is a very nice way in the sense that whenever you have unknown quantities you want to estimate and you cannot run mathematical models for their priors, just train denoisers, right? You take a neural network, you train a denoiser, throw it in, you can try to do the estimators. That was, and it could be both images and non-images, right? I showed you the for calibration problem. So when you have unknown quantities. Now, in everything I talked to you about right now so far, the images were on the grid. They're all represented as voxels or pixels in 2D or 3D. Now, the question is, can we design a plug and play algorithm to be off the grid, meaning to be more flexible, to have a continuous representation? Turns out the answer is yes, and this is very recent papers that also came out recently. You can get it online on the website. If you need a reference, you can ask me. But more information online. I'm going to skip some of the details, but try to give you the essential part. If anybody has a question, you can talk to me afterwards. But the idea is as follows. The idea is very easy. So whatever I told you so far, I represented X as a pixel values. But what I want to do is move out from this. I want to reparameterize my images. I want to say, look, instead of having the set of pixels with values, I'm going to define a neural network, fully connected neural network that's going to map coordinates XY or XYZ or XYZ time, right, to the quantity I want, okay, which is refractive index in the tomography case, which is real and imaginary, right? It could be in CT case absorption coefficient. In MRI, it would be just MRI voxel value. So whatever comes out will be represented as a function of XY. So by putting any coordinate I want, I can generate the places I want. And this is continuous representation because by changing coordinates, I can put any type of grids I want to synthesize this on. I don't have to be on a regular grid anymore. All right. And basically, this representation allows me to perfectly decouple the representation of the solution from any predefined grid, which gives me a lot more flexibility to address certain problems where I don't have a grid. Okay. And finally, I'm going to show you this application on 3D intensity diffraction tomography. But there are other applications, of course, as well that we've done, which is tomography and so on. But I think this example perfectly captures because by decoupling intensity diffraction tomography from a grid, we can handle larger data sets because we don't need to store all the voxel grid values anymore. We can just store the weights of a neural network. And by doing it correctly, you can compress to the rates pretty close to JPEG rate compression if you do it correctly. All right, so let me kind of present you the formal representation. So the way it goes is, as I said, there is XYZ grid. There's a first layer of a neural network, which is known as feature encoding. For those who don't know implicit neural representations or haven't worked with those, the feature encoding layers have turned out to be the practical trick that enables this kind of representation to work. Before, when people tried it to use just MLPs without this, the performance wasn't good. Now, the question is, what is the feature encoding layer? Usually, there are different ways to do it, but the traditional feature encoding layer is basically a Fourier series expansion. You take your coordinates and you expand them into Fourier series. We're going to have weights in front of the Fourier basis coefficients, and now they become the first layer. Those weights are trainable, right? So you have a Fourier series with trainable weights, and the rest is a normal MLP. Okay, so we have some tweak in the way we do it here in this paper, but essential idea is that you do this. Okay, so now once you have it, basically now I end up with at the outside of the neural network, I have a real and imaginary parts for the refractive index. So this could give me a 3D image. If I put in any grid here, I could form an image in principle for the real imaginary. Now, once I have this representation, the rest is easy. I'm going to use a denoiser, and I'm going to use my physics-based forward model. So here I have B illumination. So it's intensity diffraction tomography with B LEDs, right? I have B illuminations. I put them together. The A is scattering and intensity measurements. I take the data fidelity term. I'm trying to minimize this. And now here, note something. We're not the way I define this, I defined explicit regularizer here, which essentially tries to penalize the discrepancy between the input and output of a denoiser. So the D here is image denoiser. We're trying to keep the output and input close together. So what does this mean? So what happens if input is perfectly the same as output? Well, this means according to a neural network, there is no noise. Because that's kind of how we impose regularity of the solution. We try to push it closer to the fixed points of a neural network. Okay. Of course, we don't perfectly get it to zero, but we get it as a regularizer closer and closer to zero as we can. And the second thing, we try to make it as consistent with data as possible. All right. So if you would then finally minimize this over phi, which are the weights of the representation, those are the weights here, minimize it over those instead of pixel values. If you run this, now I can get something like this. By just putting in the coordinates, I can form a 3D image, right? And what's remarkable is because it's a continuous representation, I can form image at any resolution I want, right? What do I mean by any resolution? I can put denser grid, less dense grid, and so on. And now I can get different types of magnification. I can just zoom it to different regions of the image and have this continuous representation, which is nice. And I don't even have to be on the grid. I can represent it along different paths. I can deform the image. I can do all kinds of cool manipulations with this. And in particular, what this also allows me to do is to use efficient optimization scheme by, if you have a big image, you can only form parts you need to update and then do the optimization, so on. So anyways, that's a key advantage of this formulation. And then let me just show you a few examples. By the way, all the examples are also in the paper. We have compared with many different methods. You can find it up. I'm going to skip the synthetic comparison, so I'm going to show you some real data. So this is the diatom algae sample. So on the left is the reconstruction with the continuous representation that I'm going to show you. On the right is a traditional method based on Tikhonov. This is a method our collaborators have been using for IDT method all along. If you want the comparisons with more state-of-the-art methods like traditional plug and play, they're all in the paper. You can find them as well in the paper. But what I'm going to show you is we're going to go through the slices. So here I'm going to go through the slices. And for each slice, I'm showing you that cut of a 3D volume. And as you can see, it's the nice benefit of combining this implicit representation with denoiser as a prior. It gives you pretty good sectioning, optical sectioning along the optical axis. So if I go, in this case, you can see the artifacts from leakage, and here you don't see as much. Of course, another thing is you can try to zoom in and represent continuously. I'm going to skip here. This is another sample. This is a buccal epithelial cell sample. Again, the same thing. You can see here that if I go along optical axis, this one gets a very nice, clean optical sectioning ability for missing angles. And what's fun is that's one of the funnest things with this thing. I can completely synthesize frames that are not part of my original reconstruction. I can just synthesize a new frame that wasn't in the thing and try to look at them and play with this because we have a continuous representation of the object. All right, so far so good. So this is the second part of the talk. So the first, plug and play, traditional volume representation. Second, implicit representation within plug and play, which turned out to be useful for certain problems. In particular, my feeling it will be very useful for data which is on irregular grids or irregular. In fact, one place where we see a lot of benefit of it right now is through our collaboration with people doing seismic imaging, because in that case, data is highly non-uniform, and there's a benefit in this implicit representation. Now I want to go to generative models, which is going to be a wild territory because might get some people uncomfortable. I'm going to generate images consistent with measurements, but they're going to all look realistic, okay, unlike traditional plug and play. So will be limited angle computed tomography. Okay, so limited angle computed tomography is just like regular tomography. Instead, we're not going to get the full coverage of angles. So we're going to pick first 90 degrees, and then this is going to give us this kind of stretching or missing artifact. Trying to address, there's fundamentally a null space. Anything existing in there would be, in principle, difficult to recover. So here's two examples. So on the left and on the right, if I take 60 degrees here and I try to form an image, 60 degrees here and I try to form an image, can you guess what are those objects? Right? It becomes pretty tough because I'm missing 120 degrees here for reconstruction. In fact, this is a human body, maybe you have guessed, and this is a luggage. So if you try to do a filter back projection, you're going to see those images, which are very difficult to interpret because you have so much missing data. All right. Now, the tricky part here, even traditional plug and play cannot solve this. So if I would just train a vanilla denoiser the way I used to train for the past, I don't know, few years, I would get this. So, you know, it's better than this. You can clearly see that some structures appearing, but it's blurred out. A lot of features are blurred out. Okay. The reason is that regularization, the way we train it, used to be it's not a generative. It cannot try to create something new. It tries to do this kind of MMSE estimation. And turn out the trick that people have used, which is called the diffusion model, is what you need to be able to go beyond this type of images and get very realistic looking solutions, even with a lot of missing angles. So let me kind of explain you a little bit about that. So basically, this is a Dolce algorithm. Again, you can find all the technical details online. It's posted on archive. But basically, the idea is it looks a lot like plug and play algorithm, but a lot like stochastic plug and play algorithm. Okay, so how does it look like? So the starting point is, of course, the missing angle sinogram. You're going to do the first, back project the image to get the rough estimate. And now you're going to go through iterations. Okay, the iterations that we're going to look will be consisting of two things. The first thing you're going to do, you take your image, you're going to add noise to it. Okay, you start with a lot of noise. So the first iterate is just looks like pure noise. Okay, then what you do after you get this, then you do two updates. The first update will be you're going to pass it through a denoiser. I'm going to explain you how to train that denoiser. So you're going to pass this through a denoiser. And then the second step, you're going to just update data fidelity term. So try to get it. So you can do a gradient-based data fidelity term, but here we use the proximal step with respect to the current measurement. So it's a data fidelity imposition. In this case, it's basically tries to keep it consistent with our sinograms that we measure. Okay. And then at the next iteration, you're going to go back here, you're going to add again noise, but you're going to add less noise. Okay. So at each iteration, you're going to progressively be adding noise, but decreasing that amount of noise you're adding. Okay. And then finally, at the end, you're going to get to something that will hopefully be a very good looking image. Okay. This is how we do sampling or the inference. By the way, there are some constants in front of this algorithm, right? You can see this looks like a gradient descent somehow, right? But with a weird constant, those constants come from a diffusion model. You need to, the tricky part of this compared to the way I showed plug and play, I'm going to show you training in a second, that training and inference should have a matched noise schedule. Okay. So noise schedule means how much noise I'm adding at every iteration. So I'm adding a lot of noise and decreasing progressively the noise I'm adding. But the denoiser will be trained with a similar type of schedule of denoising. And that's a trick that enables this whole business to work. Okay. And then you can find more details about those constants in the papers. Let me show you how the denoiser is trained. Unlike the previous case, the way we train a denoiser is very interesting. So the epsilon will be denoiser. So this is a residual denoiser. So I'm going to add noise epsilon, and we're going to try to predict the noise essentially by then subtracting the noise. I get a clean image, right? It's a residual learning. So notice there are three things here. So this is your neural network. It takes three inputs. The first input is just additive white Gaussian corrupted noise. You're going to take an image, add noise yourself, and you're going to add noise proportional to, some sigma t. Okay, according to your schedule. You're going to add that noise. Okay. And the second thing you're going to fit is C, which we call conditioning. In our case, it will be back projected sinogram. That will be the second thing you're going to give to that network. So noisy image, sinogram, and you can also give T, which is how much noise. Essentially, it indices how much noise you're adding. And now you're going to train it for different images, corresponding sinograms, and different levels of noise. So the noise schedule going from full to left. So you're going to train that thing the same way you train plug and play denoiser, but now with different levels of noise by randomly picking noise levels and removing them. And that's the whole business. Once you train, it's still a denoiser, but now it takes T as an input. So it kind of indices the noise level. You're going to just go back, you plug it in, and you can run it. Okay. If you do this trick, which looks very simple, right? It's still a denoiser. You're going to get something very interesting. Well, there are a few interesting things. The very first thing is you can notice that as an input of the algorithm, I'm adding noise, right? Inside the algorithm, we're adding noise. What this allows us to do is to do what people call sampling. So we can, by changing the noise we're adding, so generating another noise to the same sigma, I can get another image. By putting another noise, I can get another image. So we can sample several images consistent with the scenogram that we measure. Okay, that allows us to sample multiple images. And the second thing, it will allow us to get higher. So this is the comparison of this algorithm. So the Dolce with a bunch of different algorithms. You can look at it later, but essentially the improvement is significant by doing the simple change. The improvement you can get is pretty big. Now, there are two versions of Dolce here. The first one is just generating one image, and you compute the signal to noise ratio in SSI with respect to one image at the different missing angles, so 60 degree up to 90 and so on. And the second is SA. SA stands for stochastic averaging, which means we generate hundreds of those images and average them. And if you do this, you're going to get an additional boost in performance because it becomes like sampling a bunch of random realization of those images and adding them up. Okay, so you're going to get a better performance. Now, let me show you something very interesting. So here, the human body, here's a luggage sample. And as I said, if you cut out 120 degrees, you just cannot even recognize the quality of those images because there's no missing out. Now, if you run the algorithm I showed you, you can really generate the realistic looking images, right? Each one, if you look at it, it looks like a real image. But in this case, each one is wrong. Okay, so both of those images, in particular, if you look at this thing, this is a suitcase. You know, it looks quite sharp, but there's some object here going like this. There's another object here. Those are the sample 1 and sample 2. You can see those are looking like this. But if you look at the true object, in fact, it's not exactly the same thing. So you're really generating, but it's not surprising because you're missing all that information in your data. So it's generating something plausible, but potentially wrong. Okay. But what's interesting is by generating thousands of those images, now you can actually build a variance map for each pixel, and it will tell you where your uncertainty is, right? Where your generative samples are being uncertain. And that's a thing. So this is a video of like trying to do a 3D suitcase formation, the ground truth, filter back projection, total variation, and this method. You can see it's very realistic, very sharp looking, just because it has the ability to generate images that are very plausible, right? And this is another one. This is for 90 degrees. Even better. Yeah, and that's more or less what I wanted to tell to everybody. Let me summarize my talk. I basically tried to go by introducing plug and play in a very quick way, but I think, you know, the principle behind plug and play, give you some theoretical results about it, introduced it for blind inverse problems, where now you have unknowns, which are images and non-images, right? From there, we try to reparameterize the images as neural networks and try to get the weights of those neural networks, which allows you to have a continuous representation. And finally, I showed you the Dolce algorithm, which is a probabilistic diffusion model, again, uses the denoiser as a prior, but uses it to sample images, to generate images rather than just get as one map-like reconstruction. At this moment, I'm going to thank again everybody, and I'm going to be open for questions.
Yeah, thank you so much for this excellent talk. So I will be again happy to take questions online. So for now, we start from the in-person attendees. Okay, apparently there is one question online.
Yes, do you hear me?
So we will unmute person asking question. Yes, go ahead.
Okay, I'm Christine Domal. Thank you very much for your great talk. I just have a technical question about the blind case. You showed in the convergence result, you show essentially that the cost function converges to the minimum or something, or to a stationary point, and that the two successive iterates get closer and closer, which is asymptotic regularity, right? I suppose you cannot prevent a cycling effect, nasty thing at the very, for the iterates, I mean.
Yeah, this is an excellent question, and you're right. I cannot prevent in the way I explained. There was no this analysis done, but and in fact, if you have actual errors in the discrepancy in MMSE, you will not be able to prevent it at all. But now, if you do assume you have a true MMSE saying, you can go a step further and try to go through Lojasiewicz inequalities to try to get stronger results, but I haven't done it. So you
Yes.
could try to go there, but I haven't done it. Yeah.
Yeah, okay. Yes, it's very technical and probably in practice you don't care, but okay.
Yeah, I mean, it would be extremely interesting. It just I haven't looked into that aspect of using KL inequalities, but probably stronger results could be done by doing additional assumptions, which could turn out to be mild. Yeah.
Okay, thank you.
Is there any another question? We have time for a couple of other questions.
Thank you very much for your interesting talk. My question is with the Dolce algorithm. So, because we do tomography at the Franklin, my question is, it's easy, or I mean, it's not trivial, but doable to do interpolation problems. But however, what can you do if your this sample or some of the features are small enough, unluckily, to be exactly within the missing wedge or missing angle that you can't even see? So that's extrapolation. And how do you verify that? Because you have no way to tell. If you can tell, then you already have imaged it.
Yeah, this is a really good question. You know why? Because all my career, I tried to be a magician to create something which is not there. But in that case you mentioned, there's really no way to do. Like if I take an image and cut off the part of it, there's no information about it, no method can generate, right? The best you can do now is actually just do a probabilistic argument saying, I'm going to try to get you a more likely image based on what I observe. It might be completely wrong, but that's the best you will be able to do. Now, of course, you might not be satisfied with it depending on your application, right? You might say, I really care about that detail. Then there's just, unfortunately, you need to change your sensing system if you want to get access to it. Now, luckily, in many applications, the things you could do is include some temporal dimension. Things could be, appearing in a different. In this case, not easy to put together manually by manual model. Now, Dolce type of things can become useful in that case, right? That's why I said before introducing the method, I said I'm going to be bold and generate things, okay? But in some applications, it's not.
Thank you for this very interesting talk. So about Dolce again. So I know other works of like the one from Luca Ratti in Genova, Italy. He made a talk recently in Belgium about what he does. And in particular, I remember that in the case of limited angle tomography, one of the questions is to study the kernel of the sensing operator and to do a micro-local analysis of the border of the kernel or something like that. And I was wondering if in the case of Dolce, how far can you go in the interpretation of the diffusion model? Is it that you diffuse from outside of the kernel, inside the kernel to be the most realistic with respect to the sensing operator? Is there something deeper than that? How can you, what is your opinion about that?
Yeah, so this is a good question. And by the way, for people who don't know micro-local analysis, it's mathematical tool analysis for looking at specifically CT, where you kind of look at the structure of the forward operator to try to understand how the information is structured in that geometry. I haven't done anything like this here, right? I have no connection to micro-local analysis, unfortunately. The only interpretation I could argue in that sense would be based on probabilistic model that was set up, right? So the way to interpret Dolce there is essentially, it's trying to maximize the likelihood of data fidelity to one operator, and a second then sample based on this denoiser as a prior. So it's trying to sample something probabilistically consistent with the measurements that you have. Now, it doesn't unfortunately, or just by design, take into account anything deeper about the CT geometry, the mathematical formalism of that I've seen as well of micro-local analysis. There's nothing like this considered. So there are no guarantees, unfortunately, that you could give on the solutions. at least so far. That would be amazing, interestingly work to try to bridge that and try to combine probabilistic reasoning with maybe micro-local analysis. But yeah, I haven't done anything like that. Yeah.
Okay, thank you.
One last question.
So is there anything you can say about like how you are actually sampling this space of solutions? I mean, is it like evenly spaced or like, I mean, if I assume there's a PDF on the space of solutions, obviously you can do like variance and mean which is very rough. Is there a more detailed characterization of it?
Yeah, so
by simply sampling it, yes, many times. If you see it as an ensemble of solutions, so to say, of a random process.
So I can explain you how the sampling is done. And I have to say, like, let me put a big asterisk in whatever I'm going to say. You know, our understanding of different models as they evolve, and sometimes they're incomplete. At my understanding of the ways that diffusion models still work is at best incomplete. So I'm going to admit this. It's something I'm looking at actively and we're trying to understand. But how does it work, right? So the diffusion model approach, you know, it's a technique where you train a denoiser to try to get you a score function which gets you a gradient of log of px. So gradient of log of probability of the prior. So the assumption is by training that denoiser, you get somehow access to it, which you can argue based on the mathematical formalism of MMSE denoiser, right? So now once you have it, you could just run it to stochastically sample from that probability distribution, right? Like you could do Langevin equation or so on, try to sample it. That's the original idea of the diffusion models, right? Now the distinction here is what we're doing is kind of a conditional diffusion model where I also add a gradient step, but in this case, proximal step with respect to data fidelity term. So it becomes a stochastic algorithm that does a gradient step with respect to prior, then implements a kind of decrease with respect to data fidelity term, and we iterate it until we get it. So essentially, what we're doing is something that could be created analogy to Langevin. I don't know if you're familiar with, you know, Langevin dynamics or stochastic optimization using Langevin dynamics, where we're trying to sample things from this posterior distribution of px given y. So, and then when we average those, it becomes like an MMSE estimator type of thing. Okay. Now, how do we sample? We just generate new Gaussian noise patterns that gives us another sample and then another sample, and we can just generate multiple samples. I think it's a great question. I think you could, but I don't have the tools, but I feel like intuitively you could design something better by understanding the underlying probabilistic model. And maybe people have already looked at it. I haven't looked at it, but because it's such an active field, there might be somebody who already connected it to importance sampling, which would make sense, right? Completely makes sense. But yeah, this here is just purely random sampling and then just average. So we sample like thousands of those to get that variance map and sample averaging. So